Right now, as you watch this, the closest exoplanet system is about 4.24 light-years away. And even at 20% the speed of light, a probe still needs roughly 21 years to arrive. What if I told you the hard part isn't going fast? It's not getting shredded, not missing the target, and somehow sending pictures back across 4.24 years of signal delay. Stay with me, because by the end of this video you'll understand the real roadmap to exoplanets and why the 2026 era of astronomy is turning interstellar travel from sci-fi into an engineering argument. This is where your brain rebels. We've sent spacecraft to every planet in the solar system, so another planet sounds doable, until you realize an exoplanet isn't far. It's absurd. At Voyager-like speeds, reaching the nearest star system takes on the order of tens of thousands of years, longer than recorded history. At 0.2 C, you can arrive in decades. But then a tiny dust grain becomes a high-energy impact, and every hello you send home takes 4.24 years to arrive. So the question scientists and engineers are genuinely split on is, are we actually close to a real exoplanet mission? Or are we still missing one key technology that makes the whole thing possible? To understand the future, we need the normal physics. Chemical rockets are amazing, but they get trapped by the rocket equation. If you want much more speed, you need dramatically more propellant, and you quickly end up launching fuel to carry fuel to carry fuel. That's why just build a bigger rocket doesn't scale to interstellar space. So engineers look for propulsion that doesn't carry all the energy on board. Beamed power. Lasers pushing a sail are the cleanest example. The ship becomes a lightweight payload, and the engine stays at home. This is where things get strange, because exoplanet travel isn't one problem. It's a four-part boss fight. Speed, reaching a meaningful fraction of C shielding, surviving dust and radiation at high velocity. Stopping, arriving is easy, slowing down is brutal. Signaling, getting useful data back across light years. Keep this open loop in your head. The stopping problem quietly kills most beautiful interstellar concepts. Subscribe if you want space tech that doesn't hand-wave the hard parts, because what I'm about to reveal is the three-lane roadmap: laser sails, nuclear fusion, and braking tricks, and which lane is most likely to deliver humanity's first real exoplanet data. Let's tell this like detectives, because interstellar travel didn't become serious by one breakthrough. It became serious because pressure built from multiple directions. First came the warning label. Tsiolkovsky formalizes the rocket equation. Then the dreamers got technical. The British Interplanetary Society's Project Daedalus in the 1970s lays out what a fusion probe could look like. Huge, hard, not impossible in principle. Then comes the modern pivot. In 2016, Breakthrough Starshot proposes gram-scale nanocraft pushed by ground-based lasers, aiming for about 0.2 C. The key move is that it sidesteps fuel mass by keeping the power source at home. Now add the 2026 era catalyst. Astronomy is handing engineers a better map. We're not just discovering exoplanets, we're measuring atmospheres and prioritizing targets. The catalog is huge, and the nearest systems are under constant scrutiny by ever better instruments. The universe isn't just out there anymore, it's giving us a shortlist. And the moment you have a shortlist, the question stops being, could we, and becomes, which mission architecture wins first? Here's the roadmap. The future of space travel to exoplanets splits into three paths, and the first successful mission probably won't look like a movie. Path 3 is the big ship route, advanced nuclear concepts, and in the far future, fusion. If you want heavy instruments, shielding, and long operations, you eventually want high-energy propulsion. This is the bring a real observatory approach. It's the most capable and the slowest to mature. Path 2 is the tiny and fast route, laser sails. Laser sails are the cleanest way to reach a fraction of light speed without carrying fuel. It's like windsurfing, except the wind is a laser beam. You launch many probes because some will fail. That's not pessimism, it's statistics. And that's why scientists around the world take this seriously. It's one of the first concepts that makes within decades even mathematically plausible. Path 1, the one most likely to happen first, is the fast flyby. Here's the uncomfortable truth. The first exoplanet missions are likely flybys, not orbiters, not landers, because of the stopping problem. The stopping problem is the double energy bill. You spend enormous energy to accelerate, and then you need comparable effort to slow down. If you don't brake, you scream through the target system in hours. Your mission becomes a high-speed drive-by. Images, spectra, magnetic fields, particle measurements, grab everything fast, then transmit for years. That's satisfying because it's real. It's also humbling because it raises new questions. How do you shield a wafer probe at 0.2 C? How do you aim across light years? How do you send data home with a tiny power budget? Just when you think you've got the roadmap, here's the twist. The bottleneck might not be speed. It might be survival and communication. At high fractions of C, interstellar dust is no joke. Add shielding and you add mass. Add mass and you lose speed. It's a trap that forces brutal trade-offs. Then communication. Your probe is light years away and the signal is weak. You need extreme pointing accuracy, clever compression, and likely giant receiver networks on Earth. Without that, you might reach another star and still bring home almost nothing. And this is where the controversy lies. Some scientists argue a flyby swarm is revolutionary. First, close-up measurements from another star system. Others argue it's scientifically thin unless you can brake and observe for months or years. So engineers explore braking tricks, magnetic sails that push against stellar wind, using starlight for photon braking, and even staged relay infrastructure, where earlier missions build a comms and navigation ladder. None are easy. But this is the frontier, because arriving isn't the same as exploring. I genuinely want to know what you think. What reaches an exoplanet first? A. Laser sail flyby swarm. B. Nuclear fusion probe. C. Something unexpected, braking tricks or staged relays. Comment A, B, or C, and tell me what you'd measure first. Photos, atmosphere chemistry, or signs of life. Because this matters far beyond the wow factor. Exoplanet travel is a forcing function. It pushes lasers, power generation, materials, miniaturized instruments, autonomy, and communications, tech that spills into everything from deep space missions to planetary defense. It also changes culture. A 20-year cruise plus multi-year signal delay means you build science on patience. Interstellar missions outlive headlines. They outlive careers. That's not a bug. That's what real exploration looks like. And in the 2026 era, as exoplanet catalogs and atmospheric studies sharpen targets, the pressure rises. The universe is handing us destinations worth chasing. The hopeful part is we don't need warp drives to start. The first steps are already clear. Better target selection, better miniaturization, beamed power demos, better deep space optical communications, smarter autonomy. Interstellar travel begins as a ladder of practical upgrades, not a single miracle. But this isn't the only wild frontier. Next, we'll break down how a laser sail survives launch and acceleration, the smartest braking concepts that might let a probe actually stop at another star, and which exoplanets are the best first targets based on what we know right now. Subscribe so you don't miss it. Thanks for watching. The future of exoplanet travel isn't one ship. It's a ladder of technologies, each rung making the next one possible. Stay curious, and see you in the next one.